So in this lecture, we are going to understand how processes are executed by the CPU and how the CPU switches between one process to the other, right? The stuff we are going to study is how does the OS run a process, what happens during a system call, what happens when you switch from one process to the other, and so on, right? We're going to understand the low-level mechanisms of how all of these things happen. So what happens during process execution, right? The OS, the first thing that the operating system does is it creates the memory image of a process. So what all are there in the memory image? You have the code, you have data, you have the stack, you have the heap, and so on. Okay, and the next thing that happens is the operating system in the CPU, there are various registers like the program counter and so on. The operating system sets up the program counter to point to some part of the code, and the stack pointer is pointing to the current position in the stack, and so on, right? All of these are all set up. And after all the registers and memory and files and all of that have been set up, the operating system is basically out of the way, right? The process simply goes on and executes directly on the underlying CPU, right? The program counter points to an instruction, the CPU fetches the instruction, decodes, executes, moves on to the next instruction, and so on, right? The process is basically on autopilot executing on the CPU. So it is important to note that the operating system is not involved in every single instruction execution. Once it sets it up, it is out of the picture. Okay. So now let's, before we understand how a system call works, I'd like to first explain how a simple function call works, right? Then we are going to move from that to a system call. Okay. So a function call basically translates to simply a jump in the program flow from one instruction to not the next one, but to another instruction somewhere else, right? So here is your memory image, and in your code you have, say, a call to some function, and the code for the function is defined somewhere else. Okay, so initially your program counter is pointing to this instruction, and when you have to make a function call, the program counter has to move to this instruction, has to move to the function code. But before you do that, what happens is on the stack, a stack frame is created, and this old value of the program counter is first pushed onto your stack. Why is that? Because you want to be able to return to this function invocation after you've called the function, right? So you have your stack pointer. Initially it was pointing somewhere else, then you've pushed a new stack frame, your stack pointer is updated. You have a new frame for this function call that is pushed onto the stack, and in this function call you store various things, right? You store the old value of the program counter, you store any arguments that you're passing to the function, all of that gets stored onto the stack. And once you remember where you call the function, where you should return to, once that is done, then once you save the old value of the program counter, then you update the program counter to the new value and you jump to that location, right? And once your function finishes, you have to return from the function, then what happens? You pop this stack frame, right? At the beginning of the function you have pushed a stack frame, at the end of the function you pop the stack frame, and using this old value of the program counter you return back to where you're supposed to go, right? And the stack frame, for every function call, a new stack frame is pushed onto the stack, and it contains things like the return value, the function arguments, and so on, right? So if you take a compiler's course, you're going to understand the stack and all of that in a lot more detail. The key things that you have to remember is, during a function call, the stack pointer is updated, you push a new frame onto the stack, and the program counter is updated, and both these changes are reversed at the end of the function call. So how is a system call different from a function call? It's different in a few respects. First of all, CPU hardware, all modern CPUs, they have multiple privileged levels, right? When you're running user code, the CPU has a certain privilege level set. And when you're running operating system code, you run at a certain higher privilege level with more powers, right? When you're running user code, the CPU is set to be in user mode. And when it is running operating system code, kernel code, it is set to be in kernel mode. And what is the difference? Some instructions only execute in kernel mode. So for example, if you issue a CPU instruction that has to allocate some memory, or that has to do some, that has to access the disk or access some IO device, the CPU will check, am I in kernel mode? Only then it will go ahead and execute that instruction. And if you're in user mode, it will refuse to run that instruction, right? This way, the operating system has a higher privilege level than user code. That is one difference. And the other difference is, whenever you're running operating system code, you have to make function calls and you have to use the stack. You don't use the user stack, right? You don't use the stack of the process. Instead, the kernel has a separate kernel stack when it is running in kernel mode, because for security reasons, it does not trust what the user puts on the user stack and so on. And finally, in a regular function call, the user program gives the address of the function to jump to, whereas when you're making a system call, the kernel does not trust the user to provide the correct address, right? Because the user might give a wrong address, might give a malicious address in order to do something bad with the kernel. Therefore, the kernel does not trust the user to provide an address to jump to. Instead, the kernel a priori sets up something called the interrupt descriptor table. This is set up at boot time. This has the list of all addresses of all the kernel functions for the system call, to read from disk, to write from disk, to do this, to do that. It maintains a list of all of these addresses a priori, so that when the user requests a service, asks for a system call, it knows what address to jump to already. The hardware knows where to jump to and does not have to depend on the user to provide the address, right? So in this way, a system call is slightly different from a function call. Okay, so let's now dive deeper to understand the mechanism of a system call, right? So when a system call is made, the compiler or the C library basically inserts a special trap instruction, right? When you say call read, to read from the disk, first thing that happens is a special trap instruction is run. Okay, so what does this trap instruction do? So here is your memory image and here is some code where you've called the system call, right? Say you've called read or something, and your program counter was initially pointing to this, and your stack pointer in the CPU was pointing to some position in the stack, right? This is CPU and this is your memory. So now what happens? For the trap instruction, the first thing that happens is you move the CPU to a higher privilege level. You set some bit in the CPU somewhere saying, hey, be careful, you're in kernel mode now. And then you no longer, so this is all the user stuff, and below this line is where all the kernel stuff resides. So you update the stack pointer to not stay on the user stack, but you come to the kernel stack, right? The stack pointer is updated to come to the kernel stack. And then on the kernel stack, what you do is you save context, right? You switch to the kernel stack and then you remember what is the old value of the program counter that you stopped at, what are the values of the registers. This is called saving context, right? Why? Because you have to go back. So this is what you do in a function call as well, right? When you're making a function call, you save, you remember where you stopped so that you can resume, you can return. So here also you do the same thing, just that all of this is stored on the kernel stack, okay? And then finally you have to jump to the function, right? You have to update your program counter. So the trap instruction basically looks up the interrupt descriptor table and then it figures out which address to jump to, and the program counter is updated to point to some operating system code that executes this system call, right? So all of this is done by the trap instruction. So when you make a system call, first a trap instruction runs on the CPU that does all of these different things. So a little more detail on the trap instruction, right? So the trap instruction is executed in the following cases. So one thing we've seen is the system call, right? The program needs certain services from the operating system. It makes a system call, in which case the trap instruction is run and you jump into OS code. Another case where this might happen is when a program fault happens. For example, your program accesses some memory that it does not have access to. There's a segmentation fault. You accessed an array out of bounds. Whatever, the program does something stupid and the operating system gets angry. In which case, once again, the trap instruction is called and the operating system does some damage control to prevent, to contain the damage from the fault, right? And the final case where the trap instruction is called is when an interrupt happens. That is, the program is fine, it is going on, but an external event happens. The user has typed something on the keyboard, or a packet has arrived on the network. Something has happened that requires the operating system to take some action. In that case also, the trap instruction is executed on the hardware, right? So the trap instruction is inserted into the stream of instructions running on the CPU. And in all of these cases, the mechanism is basically the same. Whenever a trap happens, either due to a system call, a program fault, or an interrupt, you do the same thing. You switch to the kernel stack, you save context, and then you jump to some address in the operating system code. You look up the interrupt descriptor table and jump to some address in the operating system code. Now, the interrupt descriptor table, of course, there's not just one function to handle all of these cases, right? You have different operating system functions for each of these things, for a system call, for different system calls, for interrupts, and so on. So how do you know which function to use? So all of these system calls, interrupts, they all are assigned a number, right? And when you're making the system call, when an interrupt is happening, this number is stored in some CPU register. So that using this number, the hardware knows which interrupt descriptor table entry to use and how to update the program counter, right? So in all of these cases, you go from user mode to the kernel mode. You jump into the operating system code. So the next thing is, how do you return from this trap, right? So a system call is made, you've jumped into operating system code and you've executed, right? So if you called a read, the operating system has started a disk read. It told the disk, hey, get me this piece of information. All of that is done. After handling the system call or an interrupt, what does the operating system do? It has to call a special return from trap instruction. So this is simply the inverse of the original trap instruction, right? It will simply undo all the changes made by the trap instruction. So it will restore the context of, whatever the program counter registers was stored in the kernel stack. It will restore the context from all of these so that the process can go back to execution. It will change the CPU privilege level. You're no longer, so when you went from user mode to kernel mode, the CPU remembered, hey, I'm doing something special, I'm at a higher privilege level. So when you call return from trap, the CPU privilege level is reset to user mode and you restore the program counter and various other registers and you're back into user code, right? You've made a system call and you're back to the instruction just after the system call so that the program can continue execution. So the user process is unaware that, all of this happened. It just thinks it called a function and it's back again and it resumes execution as always. Note that this may not happen immediately, right? For example, if you made a blocking system call, you can resume a little bit later. Or if you made a non-blocking system call, you can resume immediately. Okay. So now the question is, once you're going back from kernel mode to user mode, should you have to go back to the same process or can you go to a different process? Note that it's not necessary that you have to go back to the same process. You can also go back to some other process as well, right? So before calling this return from trap, the operating system checks, should I go back to the same process from which I was invoked or should I go back to some other process? So before we even get to the details, why should we want to do this? A process made a system call and you've come to the operating system. Why should you not go back to the same process? Why would you want to go back to some other process? So this can happen for different reasons. Sometimes when you've come into kernel mode, you cannot, even if you want to, you cannot return to the same process. Why? Because maybe the process called the exit system call and it must be terminated, or it did or there was some fault in the program, it must be terminated, there's a segmentation fault, whatever, right? You may not, the process may not exist for you to go back to it, right? The process has terminated, or the process has made a blocking system call. The process said read, and until the data from the disk is ready, the process cannot proceed. So in such cases, once you're in kernel mode, there's no point going back to the same process again, right? And another case is, even if the process is ready to run, right, the operating system may not want to return back to the same process. Why is that? Maybe the process has run for too long, right? The operating system has this responsibility of juggling multiple processes. It has to time share the CPU. Therefore, it might decide, hey, this process has run for too long. I'm not going to go back to it. I'm going to switch to a different process, right? Whatever the reason, in such cases, sometimes when you go from user mode to kernel mode, right, due to a system call, interrupt, whatever, sometimes you may not go back to the same process, but you might go back to the user mode of another process, right? So that is called a context switch. That is, you switch from one process to another process. Okay, so the OS has a piece of code called the scheduler that is really responsible for doing this context switch, and the scheduler has two parts. One is the policy, which is, once you decide I have to switch, which process should I switch to, right? I have 10 other processes that are ready to run, which one should I pick? That is the policy that we're going to study later in this lecture. Now what we're going to study is, once you've identified, hey, from process A I want to go to process B, what is the mechanism to switch to that process? So different schedulers have, there are different types of schedulers around. So one set of schedulers are what are called non-preemptive schedulers or cooperative schedulers. So these schedulers are really polite, right? They will only switch if a process cannot run, if it has been blocked or terminated and there's no way the process, the previous process can proceed to run. Only in such cases they're going to initiate a context switch. Whereas other schedulers called preemptive schedulers, they basically can initiate a context switch even if the previous process is ready to run, right? So the CPU periodically generates what is called a timer interrupt, right? You can set what this time is. Periodically the CPU will cause an interrupt and cause the operating system to come into play, right? Periodically your system goes into kernel mode whenever this timer interrupt happens, and in such cases the operating system can check. So it was running a certain process and it went into kernel mode due to the timer interrupt, and this process is still ready to run. It's okay to go ahead, it's not blocked or anything, but still the operating system can say, hey, you've run for too long, let me go back and let me switch to a different process, right? The operating system can do that. So such operating systems, such designs of schedulers are called preemptive schedulers, right? Even if a process is ready to run, you can sometimes switch away from it. When a timer interrupt happens, you can say timeout and move away from it, right? So these are roughly the two different types of schedulers. In the next lecture, we're going to study different scheduling policies, preemptive and non-preemptive scheduling policies. But right now, we are going to study the mechanism. Once you decide to switch, how do you switch, right? So let's take an example. Here is a process A, which was running, and the operating system went into kernel mode due to, say, a system call or an interrupt or whatever, and then it decided, I don't want to go back into the user mode of A, I want to switch to some other process B, right? So we are going to see how this context switch happens. So the operating system is in control, you're in kernel mode of process A. So what happens? The first thing you do is, on the kernel stack, you save the context of A, right? So you're stopping execution of A. Therefore, you remember the program counter, the stack pointer, various registers. All of these values you have to save. You save the context of A. on the kernel stack of A. And then, so your stack pointer of the CPU is pointing to the kernel stack of A, right? And then what do? You switch the stack pointer to point to the kernel stack of B. So you first save all the state of A and then you switch. You say, let me go to some other kernel stack, and you restore the context. So all the PC and registers and whatever state of B was there on the kernel stack, you go ahead, restore that context of B. So the question comes up, who set all of these registers, the PC and all of that of B? When was this context saved? It was saved in the past when the operating system switched B out, right? In the past, at some point, the OS said, enough of B, let me move on. At that point, whatever program counter and registers and all of that was saved, you switch to that and you restore from that. Therefore, wherever B stopped in the past, it's going to resume from there, right? So you're going to resume in the kernel mode of B, where you had stopped in the past when B was switched out, right? And now the CPU is running in the kernel mode of B, and now you do whatever you want to do. You return from trap, you go back to executing B's program, and so on, right? So this is the mechanism of a context switch. What is happening? You are in the kernel mode of a process, you save all the state in the kernel mode of the process, and you switch to another process's kernel stack, and you restore context from another process's kernel stack, and then you are now effectively running another process, right? And now you're in the kernel mode of B. From kernel mode of A, you went into the kernel mode of B, and now you return from trap, you run B, you go on with life as usual with process B. So I'd like to end this lecture by pointing out a small subtlety on the saving context, right? So context, what is context? It's basically the program counter, various other CPU registers that are holding the current execution of the process. So this is called context. And this context is saved in two different scenarios. One, when you go from user mode to kernel mode, right, of a process, you save context. You know, the process has made a system call. You remember where you stopped in the user mode, you save context on the kernel stack, and then when you want to return, you run a return from trap instruction, you restore that context and you go back into the user mode of a process and execute your program. That is one place in which where you store context. The other time you store context is, one is when you go from user mode to kernel mode, and the other time is when you make a context switch, right? So you are in the kernel mode of a process. Then when you switch to the kernel mode of another process, at that point also you save context. You remember where you stopped in the kernel mode of A. You remember that. You save all those program counters, everything on the kernel stack, and you switch kernel stacks and you restore the kernel context of another process, right? So there are two different times where you save context. One is when a system call, trap, system call or a program fault or an interrupt happens and you run the trap instruction. That is one time, one situation where you save context onto the kernel stack. Another situation is you're going from one process to the other. Then you remember where you stopped this process. That is the other time where you store context on the kernel stack, right? So this completes our lecture on mechanisms of how you make system calls and how you switch between processes. And the key idea here is you save the context of a process, and when you want to resume the process, you restore the context of the process.